Hello, welcome to my video series of algorithms. This is part 12 of Module 1, Sorting Algorithms. In this video, we will discuss external sorting algorithms. Recall that all sorting algorithms we have discussed so far assume that we can load the entire dataset into memory. And we can perform random data access in a constant time and with negligible overhead. For example, for an array A, we can access its data elements in arbitrary orders like A13, A3, A26, etc. by simply providing the indexes of the data elements. However, in many applications, the input dataset may be too large to be put into the memory. In this case, we may need to access the hard disk to fetch the requested data. Know that the hard disk access is very slow, and in many cases, thousands of times slower than accessing the data in memory. Thus, our focus on computational efficiency is set on minimizing the hard disk access, rather than minimizing the time complexity terms as discussed before. Therefore, we will need some special handling of such a problem. We will develop sorting algorithms that do not need to load the entire set of input data in memory. In this case, we call these algorithms the external sorting algorithms. Recall that a good external sorting algorithm should minimize the number of hard disk access. It should also maintain a reasonable time complexity for the other in-memory computations. Before delving into the external sort algorithms, we should spend some time discussing how a hard disk works. Here is what a hard disk looks like. The data is stored in the platters, or the big round disks shown in the figure. When we need to access the data, the disk is spun such that the magnetic head is placed right on top of the disk location where the data is stored. And then, the data is read from or written to the disk location, and we have completed the data access. The time needed to spin the disk and place the head into the proper location is what makes the hard disk access very slow. On the other hand, when the head is placed properly, reading or writing the data is comparably fast. In this case, most computers will read a block of data elements from the disk and load them into memory, much more than just the data element being requested. This data loading strategy is called prefetch. The rationale is that we'd assume these adjacent data elements will be accessed in the near future. For example, when we write a for loop, after accessing AI, we will access AI plus 1, AI plus 2, and so on. With data prefetch, data elements AI plus 1 and AI plus 2 had already been loaded into memory when AI is requested. Therefore, we can save many unnecessary hard disk accesses. As a result, for a traditional hard disk and some I smaller than j, accessing AI first and then AJ is faster than accessing AJ first and then AI. This is because disk spinning is unidirectional. If the head is currently on AJ, we would need to spin almost an entire circle to reach AI. However, for modern solid-state drivers, or SSD, no spinning is required anymore to locate the data. But related data elements are still stored in the same storage unit called a page. Therefore, programs run on SSD can still benefit from sequential data access, but may not be as significant as in HDD. Hence, in our model, we shall minimize out-of-order data accesses. Then, we shall discuss how the number of heads available affects our algorithm design. Sometimes, the execution of a command requires multiple pieces of data. For example, when we write C equals to A plus B, we need to access 3 different data contexts, A, B, and C. The program can run faster if we can access these different pieces of data simultaneously. Luckily, most modern hard disks have multiple read and write heads. When we need to access more data contexts than the number of heads we have, each head may need to access multiple data contexts. In this case, we will need more time to spin the disk to place different disk locations under the head. Therefore, when designing external sorting algorithms, we also need to minimize the number of data contexts that are being accessed at the same time. With the above background, we can now summarize our goal for designing an external sorting algorithm. First, we should only use a constant amount of memory, as we assume that the input data is too large to fit into the memory. Second, we should adopt a sequential data access pattern, as random accesses of data stored on a hard disk could involve substantial overhead. Third, we should try to minimize the number of different data contexts being accessed at the same time. To achieve the above goals, we are willing to compromise the time complexity if necessary. Also, since the data volume is too large, we cannot store the output in memory either. Therefore, we will directly write the sorted list into the hard disk. The external sorting algorithm we present is based on the merge sort algorithm. It also contains 3 additional improvements, namely multiway merge, polyphase merge, and replacement selection, that can boost the performance of the naive merge sort solution. In this video, we will focus on presenting the naive merge sort and the multiway merge algorithm. We will discuss polyphase merge and replacement selection in the next 2 videos. To begin with, we first know that the merge sort algorithm is ideal for external sorting purposes, as it satisfies all constraints imposed by external sorting naturally. Recall the merge sort algorithm, which has been discussed in part 7 of this module. Its key merge procedure tries to combine 2 sorted lists into one. It assigns 2 pointers to traverse the 2 input lists respectively. It then compares the elements being considered and outputs the smaller one. In the whole process, it only needs to load the 2 pointer-bearing elements in memory, thus requiring a constant amount of space. Meanwhile, the data elements in the 2 input lists are being accessed one by one, respecting the need for sequential data access. Finally, it only needs to access 3 different data contexts at the same time, which are the 2 input lists and the output list. Therefore, only needs 3 heads. As a result, we shall adopt the naive merge sort algorithm as an external sorting algorithm. Specifically, we will use 4 arrays, namely A1, A2, B1, and B2. 2 arrays hold the inputs and 2 hold the outputs, and their roles are switched alternatively as described in the original merge sort space management. Say, in the first phase, we use A1 and A2 to hold the inputs, and B1 and B2 to hold the outputs. Note that these arrays are stored in hard disk, but not in memory. Given the input data, we will first read a fixed number of elements in memory and sort them internally. Then, we write a sorted list into one of the input arrays. When deciding which array to write to, we select the array that contains fewer elements. For example, if A1 contains more elements than A2, we shall write to A2, and vice versa. After processing all data elements, we should have written the inputs as small sorted data blocks evenly in A1 and A2. Then, we iteratively perform the following steps. We take 2 data blocks, one from A1 and one from A2, and use merge sort to combine them into one sorted list and write it to B1 or B2. Again, we will write to the array whichever contains fewer data elements. After handling all data blocks, we now have larger sorted data blocks stored in B1 and B2. Now, we will use merge sort to combine data blocks from B1 and B2 and write to A1 and A2. The process repeats until all data elements are written as one single data block. Let's consider this simple example. We assume that the memory can hold 2 elements at a time. Also, note that the arrays A1, A2, B1, and B2 are stored on a hard disk rather than in memory. We begin with loading 2 elements at a time. First, we load elements 12 and 3. We sort them in memory and write them in sorted order to A1. We then load the next 2 elements, 4 and 24, sort them in memory, and write the sorted list to A2. We repeat the process until all elements are read and written in A1 and A2 as sorted data blocks. Then, we will run the merge sort algorithm on the sorted data blocks. We begin with merging the first blocks in A1 and A2, as shown by the black box. The resulting larger sorted list is written to B1. We then handle the second blocks in A1 and A2 and write the merged list to B2. Similarly, we merge the third blocks in A1 and A2. Note that A2 contains no data at this point. So, the list stored in A1 is directly written to B1. Now, all data blocks stored in A1 and A2 have been handled. We will switch the rows of A1, A2 and B1, B2 and begin to combine the sorted blocks written in B1 and B2. We repeat the same process. We first take the first blocks in B1 and B2 and combine them into a single sorted list and write to A1. We then take care of the second blocks in B1 and B2 and write the output to A2. Then, all blocks in B1 and B2 have been combined. We shall again take A1 and A2 as inputs and merge them. We take the first blocks in A1 and A2 and combine them into a single sorted list and write it to B1. Now, you can see that all data elements are now in a single array. And we are done with the sorting. The data elements that have been written into B1 are now in sorted order. We have got our very first version of the external sorting algorithm. We can count the number of context switches and estimate how our algorithm performs. When combining the sorted data blocks and writing the outputs, we strictly implement a sequential data access pattern. Context switches happen when we alter the rows of the 2 pairs of arrays. That is, we need to jump from the ends of the arrays back to the starts of the arrays. Note that when we switch the rows of the arrays, the input data block size doubles. Hence, the number of context switches we have is the same as the number of different data block sizes we have. We have input data blocks with sizes n over 2, n over 4, and so on, all the way down to 1. In this case, we have log base 2 n context switches in our algorithm. Now, if we were able to merge more than 2 data blocks at a time, say k data blocks, we can reduce the number of context switches to log base kn, which is smaller than the original log base 2n context switches. Therefore, it makes sense to consider a multi-way merge strategy in the external sorting algorithm. Consider the example again, and let's assume we'll use a 3-way merge strategy this time. Now, we'll need 6 arrays, or 6 heads, 3 as inputs and 3 as outputs. We perform the same procedure, beginning with loading size 2 data blocks from the input, sorting them internally, and writing to the 3 input arrays. Then, we take the first data blocks from the 3 input arrays. Note that we are merging 3 sorted lists this time. We output a single sorted list to B1. We merge the second data blocks from the 3 input arrays and write the output to B2. Now, since all data elements in the A arrays have been processed, we switch the rows of A arrays and B arrays. We combine the first data blocks in the B arrays and write the output to A1. Now, we are done with the sorting. You can see that with the three-way merge strategy, we only have 2 context switches this time, compared to 3 context switches for the naive two-way merge. Still, we have one question remains. How do we merge k sorted lists into one? For the naive two-way merge, we know that we shall maintain 2 pointers to traverse the 2 input lists, and output the smaller one of the 2 pointer-bearing data elements. We can generalize the task of the k-way merge. We shall maintain k pointers and output the smallest one of the k pointer-bearing data elements. Of course, we can spend linear time examining each of the k pointer-bearing elements and find the smallest one. However, we can also use the heap data structure to assist this step and achieve O log k time complexity. At this point, we can summarize the multiway merge procedure as the pseudocode shown here. In line 3, we construct a size k heap. Within the main while loop, at lines 5 to 7, we output the smallest one among the k pointer-bearing elements. In lines 8 through 11, we increase the pointer and add the next element to the heap if available. Finally, let's analyze the external sort algorithm we have so far. We will skip the correctness analysis since it is a trivial extension of the merge sort algorithm. For time complexity, we know that the naive two-way merge algorithm takes O n log n time. For k-way merge, we need to spend O log base 2k time to output each element. So, the time complexity is increased to O log base 2k times O n log base k n. For space complexity, we only use a constant amount of memory space when we load a fixed number of elements and sort them internally. In summary, we have presented the basic notion of external sorting and a naive algorithm based on merge sort. We have also discussed the multi-way merge trick and can reduce the number of context switches. However, a remaining problem is that for the k-way merge strategy, we will need 2 k-heads, which could trigger unexpected overhead. In the next video, we'll present the polyphase merge algorithm that reduces the number of required heads from 2k to k plus 1. Thank you for watching, and see you next time.